All right. Okay. So, yesterday we talked about graphing square root and cube root functions. Now, remember, we started with the parent functions, and I told you had to memorize these two tables because those will give you the basic parent function. And then from there, every other function, whether it's cube root or square roots, is going to be some transformation of these functions. So knowing those tables gives you a place to start. So we went through and did some square roots yesterday. Now let's talk cube roots. So page 30, that's what I'm on. So we start by just listing out our cube root parent table. So what does the parent table look like for a cube root function?
That's
Nope.
-2.
Nope.
0, 1.
Nope. Guys, it's not like it's not on your paper.
0, 1.
Nope. That's square root. Really?
-4.
-8. -2. -1. -1. 0, 0. 1, 1. 8, 2. It's a cube root, not a square root. Y'all were telling me square root. Now, if we look at the function itself, what transformation is going to happen? It's not going to move to the left. It's going to move to the right 5. So remember, the y's are going to essentially stay the same. Only thing that's going to happen to the x's is that since it's going to the right 5, are we technically subtracting 5 or are we adding 5? You sure? Adding 5. So guys, the reason that it's opposite in here is because the kind of how you write out the function is the same way that you do a quadratic vertex form. All right, it's just kind of just the formula for it. Same thing with the square roots. This is just kind of the general formula where HK is kind of the middle point. So that's why I say when you look at what's under the radical specifically, just ask yourself, okay, am I going left or right? And then think logically like, okay, on a number line, I would have to add 5 if I'm going to the right. All right. So I'm going to add 5 to all these x's. Now, since there's nothing outside, that means the y's are staying the same. So this is going to be x plus 5. So what's -8 plus 5? -3. Next. +4. Next. 5. Next. Next. 13. So we added 5. So we added 5 to all of our x values. And again, since nothing is outside of the radical, like there's nothing, that means the y's stay the same. So we're going to graph all that we can fit on the graph. So I have -3, -2, 4, -1, 5, 0, and 6, 1. 13, 2 won't fit on the graph, so we'll leave it off. So your graph will look something like this. Yes? The parent function you just have to memorize. So remember, the parent function for a cube root is just the cube root of x. So honestly, the x's are always just going to be perfect cubes, and I usually just pick kind of small ones that will fit on the graph. So like the largest one that'll fill in this graph is, the smallest one that'll fill in this graph is -8 as an x value. The largest will be an 8. So it's really just, you're just looking at the axes and just seeing what it is. But any perfect cube can be considered an x value here for the parent function. Yes.
Are we gonna get a delta graph on this?
Yes.
Like the question that was.
Yes. All right. So what's the domain and range of this function? It's all real numbers for both. So domain is from -infinity to +infinity, or all real numbers. Range is from -infinity to +infinity, or all real numbers. So that's usually true for the domain and range of any cube root function. It's always going to be all real numbers for both. Now, look at example 5. So notice that it's written with a raised to the 1/3 power, but we can rewrite that as a what? Cube root. So I have negative cube roots of x plus 3. So let's talk function transformation. So if I look at the x plus 3 underneath, what's happening?
Like the left one or the left right.
So we're going left 3. All right. Now on the outside, we have a negative. So what does that mean? Reflect over what?
The y.
Nope. X-axis. Now, I'm going to rewrite my parent function. So I have xy, -8, -1, 0, 1, 8, -2, -1, 0, 1, 2. So the left 3, is that going to affect my x or my y's? X. So if I'm going left 3, what am I technically doing to my x's? Subtracting 3. All right. Now, the negative, is that going to affect my x's or y's? That's going to affect my y's. So that means I'm going to multiply my y's by -1. So when I convert, I'm going to have x minus 3 for my new x's and -y for my new y's. So let's subtract 3 from each one of my x's. So what's -8 minus 3? -11. What's -1 minus 3? All right. 0 minus 3? 1 minus 3? 8 minus 3? Now, all I'm doing is multiplying -1 to my y value. So essentially, what am I doing? Flipping the signs. This would be 2, 1, 0, -1, -2. So we subtracted the 3 to the x's, and we flipped the signs to the y's. And so this table is the one that we're going to graph. So I have -11 doesn't fit, so I'll start at -4, +1, -3, 0, -2, -1, and then 5, -2. So my graph will look something like this.
For the page, did we get new journal things yesterday?
Yeah, I'll give them to you after we finish this. All right, so what's the domain and range? All real numbers.
Is it always gonna be all real numbers?
For cube root, yes. Square root's the only one where it can vary. So cube root, it's always going to be all real numbers. Square root, it varies. Mm-hmm. Typically, yes. Now, let's see if you guys can go backwards. So, we're going to write the equations of the graph functions and state the domain and range using interval notation. So first off, you got to identify whether it's a cube root or a square root function. And then you got to look at transformations based off of the parent. So my suggestion first off, identify whether it's a cube or a square root. So for example 6, is that going to be a cube or square root graph? It's definitely a square root. So I'm going to have something y equals square root. So that means that my parent function is in effect. So I'm just going to graph my parent function. So 0, 0, 1, 1, 4, 2, 9, 3. Just so I can have it as reference for how I got from one to the other. So this is my parents. And I want to know how I got from my parents to the black function. So my recommendation, just pick a point or two and see what happens. So if you look at the black, here's some of the new points. The parent function, you just got to know. Like, you just got to know the parent function. You just have to know. It's the square root of x. You just have to know that table. Like the one we did yesterday, you just got to know that table. All right. Shh, 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 shh. So how did I get from the purple to the black? We just went left 6. So we went left 6. So that means I have x what? Plus 6. Did anything else happen? No. From there, it stayed pretty consistent. So this is my function. No, not really. It just wants the original what the function is. Now, what's the domain and range of this? So look at the black function only. What's the domain? -6 to positive infinity. Good. What's the range? 0 to infinity. Good. So I'll give you a hint. It's typically the point that it starts with that kind of tells you what the domain and range is going to be. All right, next one. First off, what type of graph is it? Cube root, not cubic. So this is a cube root. So that means we're going to have something y equals something cube root. So for reference, go ahead and plot the parent function of the cube root. Now, if we also mark some points on the new function, so here, 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 and then that goes off. Here. All right, so all right, so someone tell me something that happened from the parent to the new. Up what? It went up 5 and then what? Right 2. So, guys, this is how I look at it. I pick kind of the origin as kind of a good starting point. And then because it's also kind of the squiggle point here, if you notice, it's kind of where it goes squiggle and then it goes up into the positives. So you just have to count up 5 over 2. So how do you translate that to a function? X minus 2 plus 5 on the outside. So that's your answer. Domain and range is always going to be what for a cubic? All real numbers. Any questions on how you get the equations? So again, knowing that parent function will help you honestly, if you get a problem like this on your test, graph the parent function and see what you do. Yes, sir.
So if it goes up or down, it's always on the outside of the cube.
Say it one more time.
So the function goes up or down, it's always on the outside.
Yes, because remember, it affects the y's. Anything that affects the x's is under the radical.
Could you put those 5 in front of those?
I would not. I mean, you could, but it had to be 5 plus. If you forget that plus, it's incorrect. I would leave it on the outside, on the end. Like if you notice, that's why I put a little bit of extra space in between the radical and the number, just so you can see that it's clearly not under the radical. All right. Now, there are also ways to find the domain and range without of a square root, without having to actually graph it. So let's think about this logically. We talked about this yesterday. What is the lowest possible number that we can have under a radical that would still give us a real number? 0. All right. So a square root. So with a square root, we can have a 0 under the radical and still be considered real. But as soon as we get into negative territory, that's when we start getting into imaginary, which we can't graph. All right. When we're talking graphs, we're talking about real numbers exclusively. So with a square root, we cannot be anything less than 0. So, and again, we know that the square root can't be negative because if it is, that means we're in imaginary numbers, which we don't want. That means x minus 4, so what's under the radical, has to be greater than or equal to 0. So whenever we evaluate x minus 4, it has to be greater than or equal to 0. So if I have x minus 4 is greater than or equal to 0, let's solve for x. So all I got to do is add 4 to both sides. X is greater than or equal to 4. That's the domain right there. How could I rewrite that as x is greater than or equal to 4? What's the other way I can write it if I use interval notation?
Bracket 4, comma, infinity.
Yep. Parentheses. Yep, that's exactly what you do. So either one of these I would take, unless they explicitly ask for like interval notation or inequality notation. But if it doesn't ask, I don't care which way you give it to me. So all you got to do to find the domain is set that number equal to 0. Now, the range is really easy, which we'll talk about in just a second. But for right now, we're just worrying about the domain. All right, so let's see if we can find these domains. So I'm going to set what's under the radical to greater than or equal to 0. So if I solve this, what would my what would my domain be?
-5.
-5 what? Halves. Subtract 5, divide by 2. How would I rewrite that using interval notation? Good. Now, the other one. 2/3 x minus 8 greater than or equal to 0. We'll add 8 to both sides. I get 2/3 x is not equal, greater than or equal to 8. We can multiply by the reciprocal on both sides. So that goes away. X is greater than or equal to 8 times 3 is 24. Divided by 2 is 12. So x has to be greater than or equal to 12. What's that in interval notation? Now, for domain of a square root, it's always going to be bracket some number to infinity. We don't really deal with, in this class, reflections over the y-axis. with square root functions, so it's always going to be whatever number you get under the radical, that's going to be your lowest number. All right. Range, it varies. So for this domain, for letter A, what do you think the domain is? Nope. Guys, take the number. X is greater than or equal to 0. So in interval notation, that is good. Now, the range, there's two ways to get it. All right.
Bad boy.
You're
such a bad boy, bro.
Just hole punch it like wherever you can, and then just hook it back on. Other side, you gotta flip it around. Just leave it on my desk, I'll take care of it. All right. Now, range. The easiest way to find it is to take whatever value you got for the domain, because that has to be your lowest value, and plug it back in for x and evaluate. So if you do 5 square root 0, that's still 0. So your range is y is greater than or equal to 0, or 0 to infinity. Now, the only time that changes is if you have that negative in front of the radical. If there is a negative in front of the radical, the range flips. All right, which we'll see in just a second. Letter B. Think about this one carefully. Nope. All real numbers. Why? It's a cube root. Gotta pay attention to that root. We only really care, both of these are going to be all real numbers. We only really care about the whole setting it greater than or equal to 0 if it's a square root. Cube roots, it's always going to be all real numbers no matter how you slice it. Now, C. I want to set x minus 7 greater than or equal to 0. So x has to be greater than or equal to what? 7. So that's from 7 to infinity. That's what I'm about to talk about. Okay, so think about this logically. So the negative means that instead of having a graph that looks like this, you have a graph that looks like this. So this is when you have a negative. So the range originally for this blue graph is from some number to infinity. But when you put that negative, now the range is from negative infinity to some number, because the highest value will be this point. So that's when you have that negative. All right. So again, you can just plug in 7 in for x and evaluate. So 7 minus 7 is 0. So the range is going to be y is what to 0? Y is less than or equal to 0. Because think about it. If we had negative y is greater than or equal to 0, divide by negative 1, we have to flip that sign. So y is less than or equal to 0. Yes, sir.
Why isn't the negative outside the radical affect the equation for the
Because it's kind of just assumed that, like, think quadratics for a second. The negative on the outside would technically be which value? The a value. So if you think about it this way, do you remember when we had this and we had an a value but we couldn't distribute it because of the square? It's the same concept. Technically, if we rewrote the square root, it would be x minus h 1/2 a. Still can't distribute because of that 1/2. That's why we can't affect it. Does that make sense? All right. So that means we would write this as negative infinity to 0. So you just got to pay attention. If you see that negative, you got to flip the range. The domain stays the same, but you got to flip the range. All right, letter D. What will be my domain? -2 to infinity. What will be my range? Nope. Close though. So plug the -2 back in, evaluate. -3 to infinity. If you plug -2 back in to find the y, because obviously this is the lowest point, so this is going to be the reference point. You plug -2 back in. -2 plus 2 is 0. Square root of 0 is 0. 0 minus 3 is -3. Now, lastly, E. Take in mind that negative in front. So be careful. So, what's the domain? 1 to infinity. What's the range? -infinity is 6. If I plug the 1 back in, 1 minus 1 is 0 times -2, that's still 0, plus 6 is 6. But since we have that negative, that means our graph's going to look like this green one. So it'd be our lowest value. The 6 will be our highest value, not our lowest. And that's supposed to be a bracket. So you got to pay attention to whether the front is negative or not. The domain, at least in this class, will always be some form of some number to infinity. The range, it depends on the a value. If you have a negative a value, it's from negative infinity to some number. If you have a positive a value, it would be from some number to infinity. That's how you'd always write your range. For a square root only. So this only applies to square root. That only applies to a square root. Because a cube root is always what? For both. Cube root for both, it's always going to be all real numbers. No matter how you slice it. Because it's impossible to get an imaginary number with a cube root. Any questions on this? All right. So, another thing to note, just so you guys know, just like how a vertex form of a quadratic looks, it's the same thing for a square root. Where your vertex, as we call it, which is that point without the arrow on it, that endpoint, is HK. Which, by the way, that can give you your domain and your range. H is your domain. K is your range. Same thing is true for a cube root. HK can give you your vertex, but it's not used for domain or range. It's just that kind of middle point when it does like that little squiggle and keeps going. All right. So that's it for radical graphing. Any questions on that? All right. So now let's move on to rationals. So go to page 34. Yep. So, all right, so rational functions and equations. When you hear the word rational, what do you think? So rational, what's kind of the key word in that? Well, technically it can be a decimal. It's a fraction. So rational typically means fraction. That's true with rational numbers because technically 1 you can represent as 1 over 1. So as true fractions, that's what it means by rational. Irrational means you can't represent it as a fraction. So obviously rational functions, guys, shush. Rational functions obviously means that they're going to be written as fractions. So typically, the stereotypical rational function has an x in the denominator. So it'd be like 1 over x. All right, so here's an example. Pretty straightforward. If there are 12 chocolates and 3 friends want to share them, how do they divide the chocolates? Obviously, you just do 12 divided by 3, you get 4. That's, elementary school math. Now, what if you divide 12 chocolates among 0 people? How much does each person get? Nope.
If there's no person there, that has to be.
Each person gets
How
zero.
is this a
How
parallel?
would anybody get the chocolate?
You can't divide by 0.
That's the point. There's 0 chocolate.
Does the question even make sense? No. There's no people to share it with or no people that even has it. So how can you share it if no one has it? So you can't share among 0 people. You can't divide by 0. It's what we call undefined.
How can you be the one sharing it?
So, and if you think about it, 12 divided by 0 would be, we don't know. So blank times 0 is 12. Well, this is the paradox right here. What's always 0 times anything? 0. So this is what we call a contradiction in math.
Wait, why have people made like an imaginary number for the square root of a negative, but not for this?
It's just understood that it's undefined. Even in imaginary land, it's just not plausible because of that paradox.
But if it's imaginary,
Still undefined. Undefined is very different from not real. Undefined means like no matter where you slice it, imaginary, real, complex, whatever, it's not going to be any of those values. Like you just can't do it. So, do me a favor. If you have a calculator in front of you, do 12 divided by 0 and tell me what the error type is. What does it say?
Error divided by 0.
My watch just says
divide by 0 error.
It says syntax.
Yeah, mine does not.
Unless you go to
mine says divide by 0.
Yeah, it will say divide by 0, but it will also say syntax.
Mine doesn't say.
Sometimes it'll say divide by 0, sometimes it'll say syntax. All right, so now think about it in your calculator, for example. Syntax, all right? Think about, guys. Think about some examples with syntax. Think about English. What does syntax typically mean in English? It means the structure of a sentence. Well, it's the same thing in mathematics. The structure of how you write a mathematical expression. All right? That's what syntax means. So by dividing by 0, they're saying, well, you can't do that. That doesn't make sense with a mathematical expression. That's why, like, say if you did 4 plus 3, they'll give you a syntax error because you're not supposed to have that extra plus. All right? Put it in your calculator, see what it tells you.
It's visual. It's common knowledge.
Yeah.
I got you.
Oh no, that's minus.
That's just syntax error.
That's just not how math.
Like,
I don't know why this.
I thought there was a rule like that.
Fisher, can you get the
No,
Fisher,
two negatives equal positive. Yeah, that's what I'm thinking.
You can subtract a negative.
Never mind. I realized.
Fisher, two
The negatives
positives.
are
Okay, shut up. All right. So, That being said, let's take the domains of these functions. So this first one. Okay, the first one's a quadratic. What's always the domain of a quadratic? All real numbers. Second one, it's cubic, which is all real numbers. Yes, it is. The next one is a square root. So what's the lowest x value we can have? -5. Because we can't go past 0. It goes to infinity. What about this last one? Goes from 4/5, because you said 5x minus 4 equal to 0 to infinity. We just talked about that. Now, errors on your calculator lead to domain restrictions since the domain represents the x values that are defined. All right. So, I mean, with square roots, technically, I mean, they're defined, they're just not real, and we can't graph unreal numbers. All right. But undefined, it just means it's not even imaginary. There's no way that mathematically you just can't do it. Like, it's physically impossible to divide by 0. So, look at this example. All right. So, this is an example of a rational function. 1 over x. That's kind of like the parent. It's a pretty stereotypical one. Think about this logically. What would have to be the domain?
Everything but 0.
Everything but 0. Why?
So you can't divide by 0.
Right. So the domain is all real numbers except x cannot equal 0.
Can you just say x can't equal 0? You have to include all the
Oh, yeah. Because you could also write out an interval notation, which is just from negative infinity to 0. Make sure you put parentheses because it can't be equal to 0. Union 0 to infinity.
How would you write that in like the inequality?
This is kind of the inequality notation. Because it's all real numbers except for one number, which is 0. All right. Keeping that in mind. So in other words, you're setting that denominator equal to 0. Keeping that in mind, what do you think the domain of B is?
4/3.
Right. If we set 3x minus 4 equal to 0, because we got to find the x value that makes that bottom 0, because it can't happen, we would end up getting 4/3. So x would equal 4/3. So the domain would be all real numbers except x cannot equal 4/3. If you wrote an interval notation, it's from negative infinity to 4/3, parenthesis, union 4/3 to infinity.
Wait, does that mean 0?
Yeah, 0 works because 3 times 0 is 0, minus 4 is -4. So we have 1 over -4. It's just the expression when you evaluate it cannot be 0.
So it's just finding it like the 4/3 is the
X value that when you plug it in, it'll be 0. Because if you think about it, 3 times 4/3, that's 12 over 3. So that's 4. 4 minus 4 is 0. All right, last one. Same thing. Just set that denominator equal to 0. So x cannot equal what? Yeah. -7. So your domain is all real numbers except x cannot equal -7. If you wrote an interval notation, it's from negative infinity to -7, union -7 to infinity. All right, so in other words, to ask this question, what value of x makes the function undefined? We call these excluded values. Mm-hmm. And there can be more than one. All right. When you get to Math 3, you'll do a lot more with rational functions. And they'll be harder than the ones we see now. But we're looking at the bare basic ones. All right. So functions that make x undefined is called excluded values. And essentially is that x cannot equal to 0. So you set the denominator equal to 0 and solve for x. And that gives you your excluded value. So whatever that x value is, that's your excluded value. Now, that also has some other stipulations, which we'll talk about in just a second. So, let's look at the next one. So let's say we're going to graph this function. All right. So, if we were to make a table, what's definitely the value that we cannot have for x? Right. So x can absolutely not equal 0. So whatever value we pick, it just can't be 0. All right. So in our table, if we had 0 here, it would just be undefined. It wouldn't even be graphed. Now, I like to say do 1 or 2 above, 1 or 2 below. So I have -1, -2, 1, 2. So if I plug in -2 in for x, what's my y? -1/2. If I plug in -1 in for x, what's my y? -1. If I plug in 1 in for x, 1, 2, 1/2. No. So, listen. So if I graph these points, I have 2 1/2, 1, 1. And then I have -1, -1, -1, -2, -1/2. The graph looks like this.
Oh, wait, this is the. I don't know what I do.
Now, there's a reason the graph looks like this.
Isn't it like the
Asymptotes.
Yeah, that.
So your domain is from, it's all real numbers except x cannot equal 0. All right. So that means that if x cannot equal 0, if you wrote that in interval notation, it'd be from -infinity to 0, union 0 to infinity. What's the range?
All real numbers.
Nope. It's all real numbers except what?
Yeah, except 0.
Except 0. Because think about it. Is there any value I could plug into x and when simplified it would give me 0? No. There's no value that you can plug in for x and when you simplify 1 over that number, it'll give you 0. So it's impossible to get 0. So the range is also all real numbers except y cannot equal 0. So from -infinity to 0, union 0 to infinity. Now, these right here have a very special name. They're called asymptotes. So an asymptote is a line, whether that be horizontal, vertical, or a slant, which we don't deal with slant in this class, but just so you know, it can be, that your graph will never cross. So it gets infinitesimally close, but it will never actually cross. So the asymptotes for this graph, your vertical asymptote is x is equal to 0. Your horizontal asymptote is y is equal to 0. And again, they are lines, meaning if I were to draw it on the graph, which typically when you graph a rational function, you have to, the vertical asymptote is the y-axis, which we use a dotted line to draw asymptotes. So this is my vertical asymptote. You may see me write as VA. Horizontal is the x-axis, because that's where y is equal to 0. That's your HA. And if you notice, when I drew my graph, I drew it so that it gets really, really close to both those lines, but it never crosses.
Can it be other than 0?
Yes, it can be. We're about to talk about that. Now, transformations of a graph of an inverse function. So this is typically how you would see your graph. So if it would click. Come on, it's about to die. All right, so this graph right here, that's typically the typical form you'll see a rational function in. Now, is the translation of y equals k over x, h units horizontally, and k units vertically. All right, I don't know why it says k. That should be an A. I didn't make this. All right, anyway. Vertical asymptote. X is always going to equal h. And again, that h, you flip the sign. Another way you can think about it is you set x minus h equal to 0, solve for x. You'll get the same thing. Yes? Yes.
Wait, so is it negative 8? If you flip the sign? Wait.
No, it's
Flip the sign of the thing.
Mhm.
Okay.
Horizontal asymptote is always going to be your k value. So y is going to be equal to k. It's just h and k are just general letters that we use to represent.
Or they're just like a non-taking letter.
It's just letters that are not commonly used for anything else. So like we don't use x and y because x and y for obvious reasons. We don't use e because e is technically a number. We don't use I because I is technically a number. Things like that.
Do they use T for anything?
Hmm?
Do they use T for anything?
Time.
Okay, so D and S. Just the S.
Kind of. Those are less used. S they don't like to use because it can look like fives. V, yes. Velocity. I mean, there's different ways you can write it. Anyway. Yep. We're good. Yep. Yep. Probably today if we get to it. All right. So, A tells us, so the A value tells how far the graph has been stretched from the asymptotes. And we can use it to find the corner points and start our branches. So, the way I deal with it is your A value. You always want to look for A over A and A over 1. So, whenever you're doing your branches, you take your A value and you find an x value, that'll give you the same a value on the bottom, because then that equals 1. A over 1, you try to get an x value, that'll give you 1 on the denominator, because that'll give you a. On the flip side, you do a over negative a to give you negative 1, a over negative 1 to give you negative a. These are typically like the points that you want to use when you're creating what we call your branches, which your branches are just kind of these purple things here. All right. So now you don't need to do this, but I want you guys to look at Desmos. Well, look at me pulling up Desmos real quick. So let's say I graph that exact same function that we just graphed. So all right, here's what it looks like. Pretty much looks exactly like how I graphed it on the other page. Now I'm going to put in the asymptotes. So x equals 0 and y equals 0. Now on Desmos, it's kind of cool because if I zoom in really, really close to these asymptotes, like so at some point it looks like they're overlapping, but they're not. Because if I zoom in, they're spread apart. All right. Same thing with the horizontal. If you go over a bit, it looks like they overlap at some point. But if you zoom in, they still don't cross. It will get infinitesimally close to 0 for x and y, but it will never be equal to 0. You will get 0.99999999999, or no, 0.000000000000001, or negative 0.99999. Like it will never work, ever. All right. So that's why it works. Now, let's say that I changed the a and b value. All right. So let's say I actually typed in a over x minus h plus k. And I'm going to make a slider for all of them. So if I move a, it stretches further away from the asymptotes. Let's actually put these at 0. So as of right now, this is the parent function. But look what happens when I move a. It starts getting further away from the asymptotes or closer to it to completely flipping to other quadrants. If I move the h, so I'm going to move this back to 1. Or let's do 2. If I move the h, our vertical asymptote shifts. See the vertical line? It's not moving. If I move k, the horizontal line shifts that it can't cross. Okay, so that's what it controls. So if I go back to here, let's actually start graphing it. So whenever you start graphing these, you always want to get your asymptotes first, because that'll kind of give you an idea of where your graph's going to be. Make a quick table, and then go about your business. So first off, asymptotes. What would my vertical asymptote be? How would I find it? Guys, shh. So x minus 4 is equal to 0, so x has to equal 4. What about my horizontal asymptote? It's 3. It's whatever your k value is. So I'm going to go ahead and graph that just so I get an idea of where my graph's going to be. So here's my vertical. Again, use a dotted line for these, because technically when you graph them, you don't see them, but we use it on physical graphs because it gives us an idea of where our graph's going to go. There's my horizontal.
I just wanted to give you a heads up that I did my talk to you.
Okay.
I was just wondering, like,
Do you have
we'll keep doing the grades.
You could just email me this, dude.
Oh, yeah.
Yeah, but I'm teaching a class. No.
You want me to email you?
Yeah, just shoot me an email.
But that seems like
Just email me. Bye. All right. So then, what's my hush? What's my domain?
All real numbers.
Except
Zero.
x cannot equal 4. So whatever your vertical asymptote is, that's the exception in your domain. You can also write it as negative infinity to 4 union 4 to infinity. What's my range? All real numbers except y cannot equal 3. You can also write it as from negative infinity 3 union. Ladies, hush. All right. Now, let's go getting our graph. I don't know why I drew it like that. Our table. Now, what's our A value? 2. So A is equal to 2. So remember what I said for your X value specifically in your branches. All right, you want to shoot for A over A over 1, A over negative A, and A over negative 1. So in other words, you want to shoot for the bottom values to be these numbers with whatever X value that you throw in. So first, let's start off. If I want A in the bottom, so I want 2 to be in the bottom, what number minus 4 gives me 2? 6. So that'd be my first X value. Because then what's 2 divided by 2? 2 divided by 2. 1 plus 3? 4. So that's my first point. Shh. So A over A will give you 1, and then you just got to add whatever's on the outside to it. What part?
I just like. Yeah, this is how we got to this.
Yeah.
I'm really.
I don't know how.
I know to get everything but the table. Yeah, sure.
Okay, so the table, I'm just telling you how you can get X values. It's all based off of your, I'm literally telling you, it's all based off of your A value. So if your A value is 2, you're trying to get nice numbers where you're not dealing with fractions. The only way you can do that is if you divide by itself or 1. And then you can get the negative versions of it by dividing by the negative version of itself and negative 1. So that's what you're shooting for to be what this is equal to when you plug in an X value. So for the first one, we were shooting for the bottom to be equal to 2. 6 minus 4 is 2. 2 over 2 is 1. Does that make sense?
Yeah.
So now we're shooting for 1 in the denominator. What number minus 4 gives you 1? 5. So now we have 2 over 1, which will give us 2. So what's 2 plus 3? 5. All right. Now we're shooting for the negatives. So we're shooting for negative A, so negative 2. So we want 2 over negative 2. So what number minus 4 will give me negative 2? 2. So 2 divided by negative 2 is negative 1. Let me put some separation here. So this is negative 1. So what's negative 1 plus 3? 2. And then lastly, A over negative 1. We're trying to get 2 over negative 1, which is negative 2. All right, so we're shooting for -1 in the denominator. What number minus 4 will give me -1 in the denominator? 3. So that'll be -2. What's -2 plus 3? 1. And these are kind of your reference points to draw your branches. So if I plot it, I have 6, 4. So here, 5, 5, 2, 2, and 3, 1. And then you just draw it so that it goes through these 2 points. It just gives you an idea of where your corners are. All right, that's what I mean by that. Just gives you an idea of where your corners are. So again, whenever you're doing your branches, this is what you're looking for your x values. You're looking for values that will give you a over 1, a over negative a over negative 1. Specifically, that value, when you plug it in, will give you a denominator of whatever the a value is. We'll give you a denominator of whatever 1 is. Denominator of negative a, denominator of negative 1. Does that make sense? Dinosaur, maybe? Okay, let's do another one. Okay. So, yeah. So let's start with the asymptotes for this one. What's my vertical asymptote? No. -1. X is equal to -1. So you just set that equal to 0, solve for it. All right. What's my horizontal? Y equals -4. If you don't put X equals Y equals, I'm counting it wrong. Because it's a line. You have to write it as an equation of a line.
You know what we're trying to say.
Yeah, but it's called precision. It's the same thing as doing a square root and you're doing a cube root and not putting the little 3. Huh? Oh, so whatever your h values, just set that equal to 0, solve for x. And then your HA is just that number outside the radical. All right. So that means your domain is what? All real numbers except x cannot equal -1. You gotta put the x cannot equal. Are you talking about x? Are you talking about y? I don't know. You didn't write it. I'm not a mind reader. And yes, I will be that petty and count it wrong. Just saying. Why will I count it wrong? Because equations of a line. It's not a line if you just give me a number. All right. A line is x or y equals some formula. All right. Whether that be a number or 2x, 3x, 1 over x, whatever. All right. You don't write x or y equals, I'm counting it wrong. And I'll tell you what, right now, you'll see this again in Math 3, and any other teachers that you get from Math 3 will also count it wrong if you don't put x equals y equals. I can guarantee you that. Same thing here. If you write all real numbers except for -1, I'm not counting it. You have to put x cannot equal -1 because we're talking domain. It's precision. Mathematics is all about precision. If you don't put the correct symbols, we don't know what the heck you're talking about because they can be used in multiple different contexts. We can, make our inferences, but when it comes to math, you gotta put the symbols. If you don't put the symbols, again, -1 can be used in multiple different contexts. All right, range, what is it? All real numbers except y cannot equal -4.
Why do we say except y cannot equal? Like, why can't we just say except y equals? Because that's excluding that. Right?
I mean, it doesn't really matter, except y can. Well, if we say y cannot equal, because if you say except y equals -1, I mean, you can. Either way, I take it. But you still got to put like the y equal part. So also, if you don't want to even worry about the words, just do interval notation. All right, so now let's graph. So, guys, you know, the ones that are talking are the ones that usually don't do so hot on tests, so that might say something. So, remember, we're shooting for these for our x values. Specifically, we're looking for values that give us these in the denominator. So what's my a value in this case? No. A is what?
-1.
No.
Or -3.
-3. Your a value is -3. So that means we're shooting for, when we do these fractions, we simplify them, we should get -3, we should get 1, -3, -1, and +3. Yeah. I mean, if you just remember A1, -A, -1, that's what your denominators need to be. And just think logically that makes sense. You don't want to deal with fractions, so you want to get rid of it. The only way to get rid of it is if your denominator is either the original value or the negative of the original value, or if it's 1 or -1. That's the only way that you'll get a whole number using a fraction. So we're shooting for a to be -3 in the bottom. What plus 1 gives me -3? -4. So -4 plus 1 gives me -3. So that gives me 1. What's 1 minus 4? -3. All right, now I'm looking for 1 in the denominator. So what plus 1 gives me 1? 0. So that's -3 divided by 1, which is -3. So it's -3 minus 4? -7. All right, now I'm looking for negative a in the bottom, so that'll be +3. So what plus 1 gives me +3? 2. So that's -3 divided by +3, which is -1. -1 minus 4? -5. Lastly, I want -1 in the denominator. So what plus 1 gives me -1? -2. So that'll give me +3 was +3 minus 4? -1. So I'm going to start by graphing my vertical and horizontal asymptotes. All right. So there's my vertical, my horizontal is here. And then I'm going to graph my boundary points. So I got -4, -3, 0, -7, 2, -5, and -2, -1. And if I draw my branches, it'll look like this. And there you go. All right. Try the next one on your own. Mm-hmm.
Another question.
Mm-hmm.
I'm still kind of confused about this.
Okay. So in reality, this is really what you're shooting for in the denominator. So if it helps, you could just circle these. This is what you want in your denominators. So whatever your A value is, that's what you're shooting for. So in reality, you're only going to have like 2 points because it's -1. So that means that you're shooting for -1 in the denominator and 1 in the denominator.
Alright.
Because what happens is that'll make it a nice fraction. So the fraction essentially cancels out, and you'll just add 7 to it, like a nice whole number. Yeah. Guys, where'd my pass go?
I think Mom left on the desk.
It's not here anymore. Where'd it go? Who? No.
Average is like
I just haven't taken them.
I do.
I mean, if we're, are we counting
Wait, so how do you have all of this free time and you're still like struggling to follow along?
Because I'd rather not do the whole.
Like, how are you not more see like how it's class?
I feel free when
But you
I,
have like hours of free time a day.
I feel free when I start to work.
You didn't do a single thing.
Guys, this just sounds like all this talking just means that you're done graphing. Are you done graphing?
It's not right.
All right, so check your work. Now, this one's a little bit weird because since your A value is -1, the only ways that you can get, like, obviously your only choices for the denominators are -1 or 1. So you'd only have 2 points there, but you can still draw your branches.
Can't you just use like split it over 2 because that's easy? It's 2
Yeah, I mean, you could do 1/2 if you wanted to. It's like simple fractions. Like, that's fine. But I mean, on your test, you'll mainly have A values that are not 1 or -1. So, all right. So listen up. There is a new delta math, but it covers 5.6 through 5.8. We're technically, listen, hush. We're technically not done with 5.7. I still got to teach you the equation side of it, but you can do basically all the graphing stuff on the current delta math. It's not due till Thursday. All right, so I made it due Thursday by midnight.
Obviously, with all my delta maths for unit 4, I just have like 1 or 2 problems left to do.
Okay. Okay.
I'm gonna be on site.